Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything you need to know for the upcoming test on rational and irrational numbers. So in order to understand the difference between these two, we really need to understand the different types of decimals. So we're going to start with the difference between terminating and recurring decimals. So terminating means end. This decimal here is terminating because the decimal expansion, that is the digits after the decimal, eventually end. It's 0.175, then it stops. That's what terminate means. Whereas this one here is recurring. 0.1333333, it goes on forever. In fact, that's what those dots mean. They mean it goes on forever and follows this pattern. So terminating decimals end, recurring decimals go forever, and there is a pattern to it. So if we want to write a recurring decimal like this, we can't write all of the threes. There's infinitely many of them. So we need to have a way that we can show that this is a recurring decimal without having to write heaps and heaps of threes. And what we do is we write the decimals in exact form. So for this one here, we write it as 0.13, and you put a dot or a dash over the digits that are repeating. So 0.242424, this goes forever as indicated by the dots. We write 0.24 and we put a dot or dash over the digits that are repeating. Now you only put the dot or dash over what's repeating. For something like 0.083 recurring, only the threes go on forever and ever. So we would write this as 0.083 and we'd put the dot just above the 3. So for something like this, where there's quite a few digits that are repeating, we write just what's repeating, so 0.1286. Now, you might see it written with a dot over the first and the last number, or you might see it written like this, where you put a dash over everything. These two are exactly the same decimal. Just note, whenever you're writing something in exact form, at the very least, the last number has to have a dot or a dash above it. Now, sometimes there is more than one way to write a recurring decimal in exact form. For example, these two decimals are exactly the same. Why is that? Well, you probably know that the first one, because there's a dash over the 320, it's just going to be 320, 320 written infinitely many times. So again, we put 3 dots to indicate that that pattern goes on forever. So what would be something like this? Well, in this one, the first 32 it said wasn't repeating, so we just write that. Now we're going to write this infinitely many times. This occurs over and over again. So it'll be 032, 032, 032, and it will go on forever. So these two decimals are exactly the same, 320, 320, 320, and this one, 320, 320, 320. So please make sure you understand that. Sometimes you can write a decimal multiple ways in exact form. All right, let's now look at converting fractions to decimals. So it turns out whenever you have fractions with an integer numerator, so numerator is a whole number, and a denominator that's also a whole number, you will always get either a terminating or recurring decimal. So there is a way to check which it will be. It all depends on the prime factors of the denominator when the fraction is simplified. So 3 over 40 is simplified. Now the only prime factors of 40 are 2 and 5. There's no other prime number that goes into 40. So we can be sure that 3 over 40 will yield a terminating decimal. On the other hand, 1 over 12 is simplified. 12 has a prime factor other than 2 or 5. It's divisible by 3. So this will yield a recurring decimal. But even if you can't tell whether it's going to be terminating or recurring, we can figure that out when we actually convert to a decimal. So the way that we can convert a fraction to a decimal is using short division. So for 3 over 40, we're actually saying how many times does 40 go into 3? So what we'll do is we'll add the decimal point and a few zeros. It doesn't matter if you write the wrong number as zeros. So you probably know 40 goes into 3 0 times, and there's a remainder of 3. So we put the remainder here, and we always make sure decimal point is above decimal point. So now we say 40 into 30. Well, 40 still doesn't go into 30 any times. So we put a 0 here, and we have a remainder of 30. So now we say, how many times does 40 go into 300? So if you don't know, just count up by 40s. You'll see that 40 goes into 300 7 times. 7 times 40 is 280, and there's a remainder of 20. So how many times does 40 go into 200? It goes 5 times. So 3 over 40 is 0.075. Now we stop there because there's no remainder. 40 goes into 200 evenly. So this is a terminating decimal. On the other hand, when we have 1 over 12, we say how many times does 12 go into 1? So again, we're going to write a decimal point and some zeros. Doesn't matter if you get the wrong number. So 12 goes into 1 0 times, remainder 1. Once again, decimal point above decimal point. 12 goes into 10 0 times, and we have a remainder of 10. Now 12 goes into 100 8 times, remainder 4. 12 goes into 40 3 times, remainder 4. 12 goes into 40 3 times, remainder 4. 12 goes into 40 3 times, remainder 4. And you can probably see a pattern. This is just going to keep going forever and ever. I'm going to keep getting 3s up here and 4s down there. 12 into 40 over and over again. So that's how I know this is a recurring decimal. And of course, in exact form, we know that we just put the dot or dash over the digits that are repeating. So 1 over 12 is 0.83 recurring. All right, let's now look at the other way where we convert a decimal to a fraction. So there's 3 different types of decimals we need to be able to convert to a fraction. This is terminating, this is recurring, but it has a purely recurring decimal. The digits after the decimal place are all recurring. This one's different. It kind of has a terminating and a recurring part. Not every digit after the decimal place is recurring. So we'll use different methods for them. So terminating decimals are easy. To go from a terminating decimal to a fraction, all you do is write the number on top without the decimal place, and on the bottom goes the lowest place value of 10. So 6 is the lowest place value. It's the last digit on the right. 6 is in the hundredths column, so we put 100 on the bottom. If the last digit's in the thousands column, you would put 1,000 on the bottom, and so on. Now, whenever you're giving a fractional answer, make sure it's simplified. So 76 can be divided by 4, and 100 can be divided by 4. 19 over 25 is simplified. I know that because 19 and 25 share no common factors other than 1. So that's how you do terminating decimals. What about recurring decimals? So this is one where the decimal expansion is purely recurring. Every digit after the decimal place is repeating. So what we do there is we write the digits that are repeating, so in this case 45. On the bottom, we put all 9s. The number of 9s is equal to the number of digits repeating. So because there are 2 digits repeating, we put 2 9s. So it's 45 over 99. Once again, this can be simplified. 45 and 99 are divisible by 9. 45 divided 9 is 5. 99 divided 9 is 11. 5 over 11 is my final answer. So doing these ones is a bit harder. Unfortunately, neither of these tricks from the previous 2 will work on one like this. So this one's different because not every digit after the decimal place is repeating. So this is what we do. We use the algebraic method. We let x equal the decimal that we're trying to convert to a fraction. Now what we need to do is we need to multiply this by a power of 10 so that it becomes like this. It only has repeating digits after the decimal place. So if I multiply this by 10, it will just move the decimal point 1 spot to the right. So multiplying x by 10, I just move the decimal point. It's now 6.1 recurring. Now I need to do this process again. I need to multiply this by another power of 10 that has the same decimal expansion, that only has repeating digits after the decimal point. I need to do that so I can subtract. So if I times this by 100, remember this decimal is 0.6111111. They go on forever. So if I multiply it by 100, I move the decimal point 2 spots. So 100x will be 61.1 recurring. Now I have two things here that have the same decimal expansion, exact same digits after the decimal place. So I can get rid of the decimals by subtracting. 100x minus 10x gives me 90x. Now 61.1 recurring minus 6.1 recurring is just 55. See, when we go 61.1 recurring minus 6.1 recurring, all of these after the decimal point, they will disappear because you'll be subtracting the same decimal from the same decimal. So if I have 90x equals 55, to get x by itself, we undo timesing 90 by dividing 90. So we get 55 divide 90. And once again, if giving a fractional answer, it needs to be simplified. 55 is divisible by 5, so too 90 is divisible by 5. And that's my final answer. All right, let's now look at the difference between rational and irrational numbers. So all of the numbers on the previous slides are rational. So any integer like 3, any fraction that has integers like 1 over 8, any terminating decimal like 0.225, any recurring decimal like 0.3137 recurring. All of these are rational numbers. So we saw on previous slides that any decimals like this, terminating or recurring, can be written as a fraction with integers. 3 can be written as a fraction with integers. It's just 3 over 1. So that's the idea behind rational numbers. You can write it as a fraction with an integer numerator, integer denominator. And as I said, it turns out anytime you have a terminating or recurring decimal, it can be converted to a fraction with integers. And we saw on the previous slide, anytime you have a fraction with integers, it will yield either a terminating or recurring decimal. So all those are rational. So what then does it mean if a number is irrational? Well, that means it's not one of these types of numbers. So what does that actually mean? Well, it means that you can't write it as a fraction with integers. So what are some examples? Well, some quintessential examples of irrational numbers are square roots of non-perfect squares. So perfect squares, if you've forgotten, are numbers that are the product of an integer in itself. So 1 times 1, 2 times 2, 3 times 3, 4 times 4, all of these numbers are perfect squares. Now those numbers are rational, but if you square root a number not on this list, it's irrational. So for example, we found out that 2 is not a perfect square. It's not on our list. 2 is rational, but the square root of 2 is irrational. You can take any number that's not a perfect square. 90 is not a perfect square. 90 is rational, but the square root of 90 is irrational. Other examples involve numbers like pi. So pi is actually 3.14159. Its decimal expansion goes on forever and there is no pattern. See, that's the difference. We have all terminating and all recurring decimals are rational. So if a number's irrational, its decimal expansion is not terminating and not recurring. Its decimal expansion doesn't end and there is no pattern. It's like which digit occurs in which place is completely random. So pi is an example of an irrational number. Now it turns out if you add a rational and irrational number, you get another irrational number. What am I talking by that? Well, for example, pi plus 1 will have the same decimal expansion. It will just be 4.14159 blah, blah, blah. So it still has a decimal expansion that's neither terminating nor recurring, that goes on forever without a pattern. So because of that, pi plus 1 is an example of an irrational number. Similarly, root 2 plus 1. Adding 1 doesn't change the fact that its decimal is neither terminating nor recurring. If you times root 2 by a rational number like 5, Root 2 times 5 is irrational. So let's look a bit more at the difference between the decimals of rational and irrational numbers. So you may be thinking to yourself, hang on a minute, if the decimals of irrational numbers go forever, doesn't that mean they're recurring? Recurring decimals go forever, but there is a pattern. So let's look at something like 0.789 recurring. So you know that that's 0.789789789. It goes on forever and doesn't stop. So for a recurring decimal, we can calculate pretty easily which digit will occupy any decimal place. So for example, what would be the 302nd digit after the decimal place? Well, notice here that it repeats in threes. So we see that the third digit after the decimal place, the sixth digit after the decimal place, the ninth digit after the decimal place, and so on, they're always 9. So third, sixth, ninth, and we can keep following this pattern, 12th, 15th, 18th, blah, 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 all the way up to the 300th. I can tell that the 300th digit after the decimal place will be 9. So after 9 is always 7. So the 301st digit after the decimal place will be 7, and after 7 there's always an 8 in this expansion. So the 302nd digit after the decimal place is 8. We were able to calculate that pretty easily, but it isn't the case for a number like pi. What, for example, would be the 1000th digit after pi? Well, there's actually no way to follow the pattern like we did up here. In fact, we can't really know what the 1000th digit is unless we calculate pi to 1000 digits. It turns out that the answer to this is 9, but there is no way to know that unless you know the first 1000 digits of pi. So recurring decimals, we can always tell which digit will occupy a certain decimal place, but we can't do that for irrational numbers because recurring decimals go forever, but they have a pattern. Irrational numbers have a decimal that goes forever, but there is no pattern. The digits are seemingly random. All right, let's just now look at coming up with some irrational numbers. So let's say I wanted to find some irrational numbers that are greater than 2 and less than 3. So I want to find irrational numbers between 2 and 3. Now, because 2 is equal to the square root of 4, and 3 is equal to the square root of 9, because 3 squared is 9, if I square root any number between these, it will be an irrational number. So for example, square root of 5, square root of 6, square root of 7, square root of 8. Each of these is irrational because it's the square root of a non-perfect square. Each of them will be more than 2 but less than 3. So if you have two numbers, one involving a square root, how can you tell which is larger? So for example, let's say I've got the square root of 3 and something like 1.7. So square root of 3 is irrational. 1.7 is rational because terminating decimals always are. So which of these is larger? Well, if we want to test this, we need to square this and see if we get more or less than 3. So square means multiply by itself. If you want to multiply 1.7 by itself, do it without the decimal points. We'll multiply the two numbers without the decimal points. So first we do 7 times 17. Well, 7 times 7 is 49. And then you put the 9, carry the 4. 7 times 1 is 7, plus 4 is 11. Now we're going to do 10 times 17. So we start with a 0. 10 times 17 is just 170. So you add those two together, you get 289. So 17 times 17 is 289. What does that mean for 1.7 times 1.7? Well, because when multiplying these decimal points, there were 2 digits after the decimal point in the question, there must be 2 numbers after the decimal point in our answer. So it'll be 2.89. 1.7 squared is only 2.89. It's less than 3. So that means 1.7 is less than the square root of 3, or in other words, the square root of 3 is greater than 1.7. All right, thank you so much for tuning into this video. Best of luck studying, but I'm sure you'll ace it. This has been the luckiest maths teacher in the world. Have a great day.